Welcome to the Power Rule applications video. I'm probably going to make two of these, but this first one kind of gets you started on how we apply the Power Rule and how we can use it. So the first two questions are going to be fairly simple. It's the third one where we're going to get into where I want you to be. Okay? So here's our first application. If the position of a body, so this is our position function, is in feet and the function is time in seconds, are given by this formula. What is the velocity function? Well, we know the velocity function, v of t, because everything is related to time pretty much, is the first derivative of the position function. So this is all nice and neat. Actually, sometimes the math on this is a little bit easier than it is with some of the other problems. So we're going to take the power rule. So 2 times negative 16 is negative 32. Subtract 1 from there, so it's t. Plus, there's a little 1 here, 1 times 144, and that's going to be subtract 1, it's t to the 0 or 1, and the derivative of 20 is 0. So there is our velocity function. The only thing I want you to realize is the units, because the position function, our units would be in feet. Here our unit is going to be in, because it's slope, it's our first derivative, is going to be in feet per second. I just want you to remember that when we're doing this. Acceleration, we know, is the derivative of the velocity function, or the second derivative, if you will, of the position function. So basically we're going to take the derivative of this velocity. So there's a little 1 there. So negative 1 times 32, 1 times negative 32 is negative 32. And if there's a little 1 there, so if I subtract 1, that's t to the 0, or basically 1. So this is our acceleration function, which is a constant now. And remember, the units are going to be feet per second squared. Okay, so that's just a little review of velocity and acceleration. Okay, the next thing I want to show you is maybe a pattern, and we're going to find the first 4 derivatives of this function. Now it's in y, so I'm going to let you use y prime, y double prime, that type of thing. And I want to show you that after you keep doing the derivative so many times, after a while you're going to be coming to a constant. Look what happened here. Okay, is this function right here was a second degree polynomial. We did the first derivative, see how it dropped down a degree, and then we did the second derivative, we dropped down a degree to t to the 0, so we got down to a constant function. And let's look at this one. So let's see if this works with this one here. So this first derivative is going to be y prime is going to be 3x, subtract 1 from the power. Then it's going to be minus 6x to the first plus 0, because the 2 is a constant. Now we're going to take the second derivative, so we're just going to look at this right here. So 2 times 3 is 6x, subtract 1, so this is the first power. And then this one is to the first power, if you will, minus 6, and then we're going to subtract 1, x to the 0, so that is our second derivative. Third derivative, you're going to use 3 of these little marks. This is a 1 times 6, x to the 0. Okay, so it's x to the 0, and I said, all right, so that's just 6. And the derivative of negative 6 is 0. Okay, so then the fourth derivative, or sometimes you'll see a little 4 there, but we'll do 4 marks. There's the derivative of 6 is going to be 0 because it's a constant. So if you see, I had to do 4 derivatives to make it down to 0, and you got to a constant, and then your derivative was 0. Okay, so there's a little pattern I wanted you to see. Now this next one is important because we're going to go through and basically justify why a graph looks as it does. So let's go through this. I'm not going to put it on the graphing calculator. We're going to do it all with calculus, and then I'm going to show you this in class. Now before we figure out what values of this function is decreasing, so we want to find when this function is decreasing and it's concave up. Now, I always have someone every year that says, well, I can graph it and look at it. And you're absolutely right, and I hope you do when you're done. But I want you to be able to justify it with calculus. So if a function is decreasing, I know that's our first derivative. So our first derivative right here must be less than 0, or if you will, our slopes are negative. Okay? Concave up means that talks about our second derivative. So that must be greater than 0, or our second derivative is positive, so it's concave up. So we want to know when this function is decreasing and, notice it's concave up. So here's our formula. And in order to do this, let's write on the top here a little bit all the steps, okay? The first thing you do here when you want to find out this, we're going to be using something like this. First, you're going to find f prime, or your first derivative, and we're going to set it equal to 0 because that's going to show us the intervals where it's increasing and decreasing. Because I've put that equal to 0, that means our slopes are there 0. You're going to find our turning points, our maxes and mins. Okay, then we're going to do our f prime bar. I know you don't know what that means yet, but I'll show you. And we're going to show where our original function is, where f is increasing or decreasing. Okay, because that's what f prime tells us. So we're looking for the intervals where it's increasing and decreasing. The third thing we're going to do is we're going to find, okay, f double prime, our second derivative, and we're going to put that equal to 0 to find the intervals for concavity. Then we're going to do f double prime bar, and we're going to see where where f, our original function, is concave up and down. All right, so those are the steps we're going to do. Now, if you follow through this, the math is not that difficult, but I want to show you the steps, and I don't want you to skip any. So here's our function right here, so we're going to look at it. It's a cubic function, so let's talk about this because we learned about this earlier this year. And if it's a third degree polynomial, it's odd. So I know my tails are opposite. And if you look at it, this is positive, so my right tail is going up. Okay, our right tail is going to go up in the up direction. And if I have power of 3, that means I'm going to have 3 roots. Well, okay, let's start that again. I'm going to have 2 turns in my graph because it's 1 less. Okay, 2 turns in my graph, and I'm going to have 3 roots or zeros at the max. Okay, I can have up to. All right, so let's start with this, and let's write our function here. F of x equals x cubed minus 6x squared minus 15x plus 21. And the first thing we're going to do is take the first derivative. So I'm going to do f prime of x is going to be 3x squared minus 12x minus 15. Now we're going to set it equal to 0 to solve for this, to find our intervals where this is increasing and decreasing. So when I put this equal to 0 here, I see I could factor it out of 3. So when I do, I have x squared minus 4x minus 5 equals 0. And then I'm going to make my big T, so it's going to be actually a couple here, all right? And I have x, and if I factor that, it's going to be minus 5 plus 1 equals 0. So I have 3, which will never equal 0, so thanks for playing, we won't use you anymore. Then I have x minus 5 equals 0, so x is going to equal 5. And x plus 1 equals 0, so x is going to equal negative 1. Now, I just found where the x's are equal to 0. So at x is 5, the slope is 0, because that's what we just did. When we put this equal to 0, we said, okay, at 5 on my graph, the slope is 0, so there's going to be a turn there. And at negative 1, the slope is 0, so there's going to be a turn there. I just want to let you know what you found, okay? Now, we're going to kind of graph this over here on the side as we go along to get set up. And I'm not going to actually sketch the entire graph until we're done. So I'm going to make this kind of big. You have a whole page here, so make it nice and big. So here's, oops, undo. All right, so here's our x and our y. And underneath here, we're going to do our f prime bar, and it really does look like a bar. So here's our f prime bar. And we're going to talk about our f double prime bar, so we'll put that right underneath that. And let's look at what we have at 5. Okay, so we're going to go 1, 2, 3, 4, 5. So at 5 we found that the function is got a slope of 0, and we found it negative 1. Okay, so when I do that, I come right down, because this bar is really a number line, so there's negative 1. I'm going to come right down and call this a 5. And I want to find what our graph is doing in between there. So I want you to listen to me carefully and watch what I'm doing. I usually go to this point right here. So I'm going to highlight this where it's in factored form. And I want to know what my slopes are doing before -1, between -1 and 5 and here. So I'm going to pick a number. Let's pick -2. Now if I put a -2 in the x spot, that would be -7, and that would be negative. So a negative times a negative would be positive. That means all my slopes in here are going to be positive. Now, you can actually graph this on your graphing calculator and look at what your slopes are, and I'll show you that in class, but I want to show you this method first. Now, between -1 and 5, I'm going to pick 0 because it's an easy one. If I put a 0 here, that'd be negative, and a 0 there would be positive. Negative times a positive are negative slopes. And if I had over 5, like let's put a 6 minus 5 is positive times positive, my slopes here would be positive. So what does this mean in our original function? Well, our original function is increasing, then it's decreasing, and then it's increasing. And at these 2 points, there must be a turn of some sort because the slopes are 0. Okay, so that's what we just found. The next thing we're going to do is f double prime. So we want to talk about concavity, so we're going to do f double prime of x. And when I do, I'm going to take the derivative of our function right here. So that's going to be 6x minus 12. And the derivative of -15 is 0. We're going to put that equal to 0 to find out where the places change in our concavity. So let's do that. So I see I got 6x minus 12 equals 0. Add 12 to both sides. So 6x is going to equal 12. Divide by 6, x is going to equal 2. Now this means this is the change in our concavity happens at x is 2. So here's 2, all right? And I'm going to come down on this bar, our f double prime bar, come down here, this is our 2, and we're going to talk about if it's concave up or concave down. Okay, so again, I want you to go back to this, and you can go back to factored form or whatever, but we're going to look at numbers to the left of 2 and to the right of 2 to see where our concavity is. So if I go to the left of 2, all right, and I pick a 1, for example, 6 times 1 is 6 minus 12, so that's negative. That means it's all negative to the left of 2, so this means it's concave down to the left of 2. If I picked a 3, for example, put a 3 in here, it's 6 times 3 is 18 minus 12, that's positive, so that means it's concave up. Now, this is really, really interesting. Now we can kind of sketch this graph just from looking at it. So we know our function's increasing and it's concave down, and I know at -1 there's a turn of some sort, so I'm going to kind of draw it like this. It's going to come up, all right, and there's got to be a slope of 0 at -1. Then it's going to decrease from 1 to 5, and at 5 there's probably going to be another turning point of some sort. Let me erase that a little bit. Okay, and at 5 there's going to be a turning point of some sort. Oops, I'm not writing this very well. Let's try this again. Okay, and then it's going to increase again. So this is a really wiggly graph, but let's look at what we have here. At -1 and at 5 our slopes are 0, like we said. Our function's increasing, then decreasing, then increasing, like we said. Look at the concavity. It's concave down to about 2, and then it switches concavity and goes concave up. Now you can graph it and look at it, and you would see that your graph, if you fix your window, looks very similar. But we really haven't answered the question yet, because the question said, when is our graph decreasing and concave up? So let's look at decreasing. So our function is decreasing here, and it's concave up here. So where do they both happen? Well, they both happen between 2 and 5, where it's decreasing and concave up. So you see where they overlap. So the answer to this is going to be, so our answer is our function is decreasing and concave up on the interval from 2 to 5. Or you can say x is less than 2 and 5. I prefer interval notation, so I can say between 2 and 5 our function is doing that. So this is really interesting, and I wanted to show you that. So that concludes this video.